Okay, so we kind of mentioned this earlier, and last couple slides. Can you guys? Oh, Abby, can you guys see my slides?
Yes.
Okay. So we had mentioned that depending on temperature, we can control what aspect of what products we're going to end up with, right? So if we kind of slow down the reaction by lowering the temperature, then we're going to get what we call our kinetic product, right? So 80% of this product will be produced, and then 20% of our thermodynamic product, okay? So if we speed up the reaction, then those numbers are going to change. Okay, and if we also take a look at it, right? So in this context, this is a complete reaction. You get both of those products, but again, one at 80%, one at 2%, and it's driven in a single direction. Where in the other case, it's going to be in equilibrium when we increase the temperature. So, but then we're going to be favoring our thermodynamic product. Okay, so again, why was this the case? Is because that temperature, right? It affects that the Gibbs free energy, and so, and then it's going to give preference to that thermodynamic product, where the kinetic product, that slower product, is going to be being made with in a sense lower Gibbs free energy. So if we take a look, so kinetic control. So in terms of kinetic control, it's not going to be an irreversible reaction in this case. So it's being driven in a single direction. And then, so you're going to get the one that's the most abundant one is going to be the one that happens fastest, right? And so in that case, you're going to get more of B than of C. Although you're producing C, that reaction is going to be a slower reaction. Okay, so this is actually taking into context the kinetics of it, right? So at that temperature, you're slowing down the reaction enough that you're favoring product B and not C. So in this case, this will be our kinetic product. So those lower temperatures, the kinetic product is going to be favored because that reaction is going to happen faster at that particular temperature, right? And then as we up the temperature, we get the product that is going to be more stable, right? So in this case, we have A going to B, but then B can go back to A, and then we can get A going to C, okay? But in this context, C is more stable. So because C is more stable, you're going to get more of C being produced because of the stability of it. Okay. Does that make sense? Yeah, no, maybe. So we go back to these products. This guy is the more stable product, right? So we have more of this being produced. We know that the terminal double bond is less stable than the central double bond, right? So it just confirms that that's the case. And then, although we do know that also that terminal bromines at the end, they're typically a little less stable than internal bromines, but that double bond being here makes this guy more stable than this guy. Does that make sense? Yeah, because you remember prior chapters when we were talking about the alkenes, and when we had alkenes at the terminal end, meaning, do you guys know what I mean by terminal end? The very end of the hydrocarbon, right? So when we had the alkene at the terminal end, that was less stable than having it central, right? So, oops. So take a look at the double bonds here. Right, terminal. So this guy's going to be less stable than this guy. Okay. So again, when we look at the thermodynamic control, we're going to be looking at stability. Who's the one that's going to be more stable? When we're looking at kinetic control, that's going to be the one that happens fastest, right? Faster reaction. Okay. Okay, so in the case of the more stable alkene, has the greater number of alkaline groups bonded to the sp. So in other words, since this guy is a center double bond rather than a terminal double bond, it's going to be more stable because this guy is bonded to this sp and this guy is over here is bonded to this sp, where this is terminal, right? So it's going to be less that's going to be bonded. Okay. So initially, if we look at our two products, right? So this is a secondary allylic carbon, and then this is a primary allylic carbons, right? So secondary on a secondary carbon, and then this guy is a primary terminal, right? So in this case, we're going to have plus being located on our secondary. This one is going to be located on the primary, and then as a result of that, we're going to get the bromine sitting on here. Now, this reasoning, right, initially, because we know that our first instinct is to say, well, because this guy is a primary, or the bromine is being added onto the primary carbon, this guy is going to be less stable. But that's not the case in this situation. Instead, this guy is the less stable, the addition of that internal bromine, right? And again, it has to do with that double bond, okay? So in this case, we're going to get, again, that partial positive, that partial negative happening in this situation, partial positive, partial negative happening at that terminal situation. But we know that the production of the kinetic version, this guy here, is going to occur faster than this one, because this is, it's easier for the bromine to attach here than it is to attach at that terminal end. Okay, so it takes more. We have to get that transitioning state for this to occur. So this guy is an easier product to generate. So kinetically, this guy is favored, where thermically, this guy is favored. Okay, does that make sense? Okay, so it has to do in reality of the proximity. Okay, location, in other words, right? Due to proximity, this guy's going to form faster than this guy, right? Than that terminal end. Okay, so here's another example. So at negative 78 degrees Celsius. So in this case, you're going to have resonant structures, both resonant structures that are going to be contributing, right? But this one, again, is going to be favored due to proximity. This is, easier to get to or get at than in this situation, right? So then the kinetic product is going to be this guy. And then again, this guy is going to be a thermal. Oh, wait. Yeah. Okay. So there are cases where you're going to have products that are going to be both faster and then also thermally dynamic favored. Okay. So here's an example of that. So if we had methyl, 4-methyl, 1,3 pentadiene reacting with bromine. So let me clear this. So in this case, the favored is going to be the bonding on the second carbon compared to bonding, making a more of a tertiary structure on the 4th carbon. Okay, so in this case, you're going to have both the kinetic product being favored and the thermodynamic product being favored. So we can't always assume that if one is the kinetic product, then the other one is by default the thermodynamic product. We have to pay attention to proximity. We have to pay attention to stability. Right? So this molecule is going to be more stable than this guy. Right? So then that explains the thermodynamic component. And then kinetically, proximity-wise, this guy's easier to get to than that guy is. So. SP2, right? The SP2, and it's more stable. Okay, so the thing is that in this context, what would be the SP for this one? It's already at SP2. It's not reaching its SP2, so it's already there, right? So because we have that methyl group, right, it's going to be less, kinetically, it's going to be less appealing because you have a double bond, methyl attached to another methyl group, right? So you're doing methyl-methyl, see? Methyl-methyl, right? At this end, double bond, okay? Where we have a double bond over here. And so it's easier for it to, get to this carbon compared to this one because you're surrounded by dual methyls, right? So that carbon center, you have a methyl-methyl interfering with whether or not it's going to be accessible there, right? So this double bond is easier to get to. So kinetically, it's going to be favored, right? Thermally, it's going to be also favored because it's, in this case, this guy is going to also be more stable than adding it to this end because, again, it's going to be harder for it to get to this point, right? So time-wise, it's easier for it to put something here because of that double bond, right, on the second carbon there, rather than putting it on the second carbon here, right? So if you have the two, okay, so do me a favor, do you guys have your models with you, anybody? Yours in the car. Don't worry about it. So we'll just try it out. So, okay, so right now, this is what we have. We have double bond C. We have methyl group here, right? Which is surrounded by oops, C. Okay, CH. So I'm just going to do this. C. Okay, so in this case, you have kind of like a shielding effect or steric hindrance for something trying to get into that region, right? So it takes more effort for it to try to get into that region to sit there and bond with that product, right? So this product is going to be less accessible, right? So that's going to affect the kinetics, right? And then also in terms of stability, this double bond is already more stable than, let's say, this terminal double bond because you have that shielding effect. Okay, so you're going to have less bonding at that point or less interacting to make a bond at that point than anywhere else. So then that means that this double bond is going to be more accessible, right? This double bond is going to be more stable because you already have those methyl groups surrounding it. Okay, so in that case, you're favoring both the kinetics and you're favoring the thermal. Yeah. Okay. I mean, does it make sense? Okay. So when we exactly, and so and we need to be aware. I mean, that's the whole concept of, when we talk often about the orbitals and everything like that, but you also have other elements that are going to play a part in that, right? And so if you're blocking a part where it's not able to get access to, right, then it's going to be harder for it to act on those parts, right? And that's really what happens when we have branching that occurs there. I mean, it happens, but it happens much, much slower than in this case, right? We also know that by us having that methyl group there makes it more stable. This double bond seems to be more stable than it would be than the other double bond, which doesn't have that methyl group there, right? And you guys remember when we did the stability chart where, this one is greater than this one. And, anytime that we had a hydrocarbon attached next to that double bond is more stable than, let's say, a double bond that didn't have it, okay? So we want to remember to build off of that, right? And so we need to be able to extrapolate to that next level, Does that make sense? So we want to try to pay attention to those little scales. What I recommend is like make a little flashcard with it, because then you'll remember who has more stability, right? And then if you're reacting, your reactions is going to occur when things are going to be, quote, less stable, right? So that's going to be your point where you're going to have more reaction because you want to try to find stability in those cases, right? Because remember, the goal is to try to be stable, right? Okay. So in this case, right, if we do this reaction, well, both of these guys have the same stability. Can I erase this? Okay. So in this case, we're going to have most likely equal parts of both of these occurring, because this situation, again, same stability. Okay. The only thing is that in this case, since this guy is going to be considered to be, well, I should say, thermodynamically, they're going to be comparable to each other. Stability wise, right? This guy, I mean, they both have the same stability. This guy's going to be favored more so by proximity in this case. 1, 2, 3, being on the third carbon rather than being on the second carbon over here. 1, 2. Okay. So, or 1, 2, 3, 4, 5. Okay. Is that somebody knocking? That was you? Okay. So kinetically, yes. So that's right. So that's why this guy would be the kinetic product, right? But thermodynamically, they're going to be comparable to each other because they're both stable, right? So thermodynamically, you're going to have 50 of this and 50 of this. Kinetically, this guy is going to be easier to make than this guy, or faster, not easier, faster to make, even though that they're both accessible, right? They both, in terms of stability, they're both stable. This guy is going to be favored more by proximity because it's quicker to get to, right? So it's going to be favored that way. So yes, you're right. Okay. So when we have the Diels-Alder reaction form, so in this case, we're going to be forming a ring structure. Okay. So we have a conjugated diene, and then we have a diene phenyl, right? So as a result of that, we're going to end up with the formation of a ring structure. So we get 1, 2, 3, 4, 5, 6 carbon. We're going to preserve one of the double bonds, and then we're going to add on that additional hydrocarbon outside of that ring structure. Okay, so the way that this is going to work, okay, so here's our conjugated diene. It's going to add double bond here is going to act here. This double bond here is going to be moved here. Then this is going to result in the double bond being disrupted and then attaching to a single bond. So we'll get this guy is going to be a single bond. This guy's going to be a double bond. This guy's going to be a single bond. This guy's going to be a single bond. And then, of course, we lost that double bond. Now, if we look at the resonance structures, right? So then single, and these are going to be the potential of having electrons move from this part to this part, or this part to this part, or the formation of this bond. So as a result of this, we're going to end up with just our 6-ring member and then a double bond located on the opposite end of the carbon chain. So this is called a pericyclic reaction. And it's going to take place because you're actually shifting those electrons that are in those double bonds. Okay. So, and to be more specific, this is a 4 plus 2. So 1, 2, 3, 4 plus 2, 1, 2 cyclic reaction. Okay. So a concrete example of this, or a semi-concrete example of this. Okay, so 1, 2, 3, 4, 4-carbon chain. So in this case, the double bond is gonna offer the electrons that are going to be added onto that 4th carbon. Then that 4th carbon is then going to cause the double bond here to shift over to the between the 2nd and the 3rd. And then that causes the double bond here to use its electrons to attach to the carbon on the other structure. Okay, so we get bonding between the 1st carbon and the carbon over here. So, okay. Questions? So let's see. So if you're asked about the formation of a ring structure, right? Let's say we're going to make we have okay, let's say we have this reaction occurring. So what would we expect the product to be? Okay. 1, 2, 3, 4. Okay. I'm horrible at this. Too many. There you go. 1, 2, 3, 4. So you said 1, and then you said 4. 1, 2, 3, 4. Okay, or 1. Okay. 2, 3, 4. Yeah. 1, 2, 3, 4. So yes. So it would be 4 propyl, 1 cyclohexane. Yeah. It kind of worked out perfectly both ways, didn't it? Okay, so in this case, yeah, just heat in this case. So just heat was going to be the, yeah. So it's not going to take much. And then the key is that you're also going to have that transitional state, right? That formation of the resonance structure. So you end up with, in this case, 6 pi electrons. Okay, so something's wrong. Hold on. Okay, an electron withdrawal. So when we're withdrawing electrons, that's going to increase reactivity. And so here, electrons are going to be withdrawn from the oxygen group here. So in this case, double bond is going to cause, it's going to donate its electrons to here. Then this double bond is going to donate its electrons here. And then as a result of that, we're going to end up with a negative charge here. And then this guy's going to end up with the positive charge. So the resonant structure or the resonant hybrid here is going to have a partially negative charge and a partially positive charge forming as a result of that. And then the electrons are going to, as you said, being shifted from this point to that point. So this here, 2 resonant structures, this would be the resonant structure hybrid of the 2. Okay, so in this context, right, so we have our double bond here, right? And then, so if we're adding this structure, right? Hold on, double bond. So in the case of a double bond here, so we're not going to have that electron withdrawal occurring in the case of just the hydrocarbon. As soon as we added that oxygen off of that carbon, then that's going to end up with a withdrawal happening. So we're going to get the formation of our resonance structures, right? And so we're going to end up with that partial positive and partial negative on that resonant hybrid. And then the same thing is going to happen in the context of the nitrogen. But in this case, it's going to be a quite more dramatic. So because we have the triple bond existing here. And so as a result of that, this guy is going to be more reactive than this guy, right? So in terms of reactivity, this guy is going to be more reactive because you're going to have electron withdrawal happening. Okay. So this is just another example of our Diels-Adler reaction. So in this case, same thing is going to happen. We're going to end up forming our ring structure, and then it's going to be attached to this keto. So that would be an ester, a diester product. So in this case. Okay, so here, this is just basically showing you that an alkene can be the dianophenol. And so we could end up with our ring structure forming two or a diene ring structure, okay? And so we can, two things that we want to remember from this. One, can you guys double bond here? Just the fact that you have a double bond within that ring structure is going to allow, with the addition of heat, is going to allow for you to form this alkene attaching to the double bond, right? Even though we have structures at both ends, right? So we're still capable of forming that ring structure. It's going to happen, okay? And then the other thing is that in the case of the triple bond, you're just going to be using just one of the bonds to sit there and initiate that product starting. Okay. So if I have something like this, what would I expect the product to be? Ooh. Okay, what do you guys think? Again, 1, 2, 1. 2, 3, 4, 5. So, 3. Okay. So you said 2, 3, 4, 5, 6. 6 methyl. Cyclo-hex. N. And you said 1 all. Okay. Is that correct? You think you might be wrong? Do you guys agree or disagree? And it needs the A because you're separating the 3 and the EN. Yeah. If you didn't have, let's say if we didn't have a 3 here, right, and we put EN there, right, then you wouldn't need the A. Okay. So now you guys know what Diels-Alder reactions are, right? Okay. So if we look at the molecular orbital description, so we're going to have to consider the HOMO and the LUTO of the reaction. So this one, HOMO, means the high orbit molecular orbitals. So in this case, these are going to be your high orbit molecular orbitals. And then these guys are going to be your low. Okay. 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 And so if they have the same color, they're going to have overlap. If they have different colors, there isn't going to be overlap. So in this case, these guys are going to overlap with the same color. And that's going to be an in-phase overlap. And that's the same thing that's going to be happening over here. Okay. So okay. So in the case where we don't have reactions that are no longer symmetrical, so earlier we had those nice, beautiful products where we had the diene, the beautiful diene, whereas at the end here, we have something located at the end of our conjugated diene, right? So we're still going to end up with similar type of products, but now we just need to pay attention to where things are going to be binding at, right? So these are going to be the two products that we can get from the structure. So we can get one where, again, the double bond is going to be transferred. So we get this double bond transferring its electrons here, double bond being transferred here. And then this one is going to be bonding here, providing these electrons here. So we're going to get this structure. And then we can get the flip of that. Okay, so in the case where this guy is flipped to the other side, or okay. So if we look at which product is going to give us more, which is going to give us more product. So in that case, those partial charges are going to play a huge role in that orientation. Okay, so if we look at our resonance structure, so we end up with a plus and a minus here. So then we get a partial negative for this guy and partial positive for this guy, right? And then this guy is going to be partial positive up top, partial negative. So then this structure is going to be more abundant than the other structure. Okay, so we expect to get more of this one and less of this one. Okay, because of that, because of our resonance structures, that plus, that minus, that gives us that, when we take the hybrid of the two resonance structures, it's going to give us that partial positive and partial negative. You guys with me, or am I just talking?
We're with you.
So if we look at, because both, okay, so we look at the resonance structures of both of these guys, right? This one isn't necessarily more stable than this one, right? So actually, I think this is the other way around. This guy is going to be slightly more stable than this resonance structure, right? And it's just the fact that your resonant hybrid, the fact that you have both of those existing, it's going to favor one product more so than the other. Do you understand? Or so let's say if, for instance, right? Right now, if we look at, because it's all a result of electron being withdrawn, right? So these electrons are being passed on here. This guy's being passed on here. These guys are being passed on here, right? So then that means in terms of the resonance structure, right? So that means that this guy's going to end up with a negative charge. This guy's going to end up with a positive charge. Is this guy is not going to be more stable, right? Having a positive charge on oxygen isn't going to be more stable than not having a charge at all, right? Because normally we want that positive charge on a carbon or on something that is going to be less electronegative than the oxygen. Oxygen is more electronegative, right? So if we're talking about stability, right? Oops. So, but instead, right, we get this guy, this whole thing here is going to have that partial positive charge, right? A less stable moiety, right? And then this guy, you're going to have your negative charge on your oxygen and then your positive charge on your carbon, right? A more stable one, right? So in this case, it's just looking at our resonance structures more so than anything else, not stability, because this guy is going to be clearly less stable than this resonance structure, right? Does that make? Okay. So, but just the fact that you're getting that positive partial and negative is going to make it a little more appealing. It's going to cause that orientation to fit, right? Where if we go back, if we went the other direction, right, it's going to be positive on positive, right? And it's going to be, you're going to have less of those. So you'd have to wait for the other resonance structure to occur, right? Because when we think about the hybrid itself, the hybrid is going to, well, best way of saying this. So the hybrid is going to be the combination of all possible resonance structures. Some resonance structures are going to be more favored than the other, right? So even with that hybrid, there's going to be, okay, we have a lot of them that are going to be like this, but more of them, less of them are going to be like that. So you're going to get both products, right? But you're going to get both products. This one, even though it's less stable, having that positive, negative, right? This guy's going to occur less, but it's going to be more attractive because this guy, that separation of charge, right, is also going to have, well, it's going to be less, but they're going to be more attracted to each other than having this moiety and this moiety, which doesn't have any attraction towards each other. Does that make sense? So them finding each other are going to be more likely than the ones that don't have charges or partial charges associated. Okay, so that's what I'm saying. If we looked at the resonance structure, this resonance structure is more favored, right? More abundant. Okay, so if things are moving around, we know that electrons are constantly moving around, you're going to have this resonance structure, right? And that's the same thing here. This guy is going to be more abundant. But these two guys coming together are relying more so on this one. So you're going to get more of these guys coming together than our other case where it's flipped, right? Because there's nothing that's really pulling those together. Okay. Does that make sense? I don't know. You guys, let me see if I can figure out another way of explaining it. Okay, so let's do it like this. So in solution, we have this pink guy, right? Pink guy is going to be neutral, right? Pink guy is going to be neutral. So we got a lot of pink guys, right? Okay, now we got orange guys. Let's do green instead of orange. We have green guys. So green guys have a positive and a negative, right? Positive and a negative, right? But there's only a few of them there, okay? And so this here represents, let's say, this moiety, or we'll say this here represents this guy here. This here represents that guy, okay? So on the other side, we have blue. We only have a few of those, but they're going to be minus, plus, minus, plus, right? And then we have a whole bunch of black that are neutral. Now, if these guys come across each other, nothing's going to really attract them to each other. They're just going to pass by. There's nothing that's connecting them. But if these guys come across each other, what's going to happen? They're going to attract, right? And so these guys are shifting to these guys, but it's at a lower frequency. You have a lot more of these guys that are neutral than these guys, right? These guys are shifting to this guy, but you have a lot more of these guys that are neutral than these guys. But this adds on to them coming together and reacting. So it's going to increase that particular product. Where the other product, which doesn't have anything that's kind of pushing them or driving that reaction, right? That attraction, it's going to be less abundant. It's going to happen, but it's going to be much less frequent. Okay? Because it's going to rely on one guy's going to be positive and negative, and the other one is going to have to be neutral, and it's going to have to induce something to happen to the other guy. So this guy has to induce this guy to do something for it to happen. So you're going to have less of that product. Okay. So you have a combination of those intermolecular forces that are kind of helping with those reactions. You guys remember that? When in doubt, intermolecular forces. Okay. Okay, so what happens if we have trans versus cis? So here, this is our trans conformation. This is our cis conformation. You guys remember? And so we know that this one is, oh, yeah, that's kind of sexy for our reaction, right? So what's going to happen when we have a trans molecule, right? So it has to be in the cis formation for it to happen. Okay, because the transformation is facing the other direction. It's not going to allow for that to happen. Okay. So in this case, these guys are too far apart from each other for the reaction to occur. So they always have to be in the cis formation for it to happen. Okay. So trans, we're not going to get that to happen. We have to be in cis. Okay. Okay, so this guy's going to be locked in the cis formation, right? So this guy's in cis formation. And so if we have this guy, right, then we're going to have double bond, and then we're going to have another cyclic ring added on. So here's 1, 2, 3, 4, 5. Here's that 1, 2, 3, 4, 5. And then these are your addition, right? So that's that ring added on between the 1 and the 4. Okay. And again, so if we take a look, our favorite is going to be this guy instead of our flipped moiety. Again, because you're going to get that partial positive and partial negative that are going to be happening. Okay. Question. And then it's also because you have this locked. S6, S-cis structure. So we're going to end up with a bridge bicyclic compound. And this is just showing you that structure. So this is where you're going to get your attachments. And then you're going to have two rings that are going to be shared. And two of them are going to be at the non-adjacent carbons. Where this guy has, it shows us two rings shared, but we have two adjacent carbons. So adjacent here. So this is a fused and this is a bridged. Okay, so the next thing that we have to be concerned with is endo and exo. If it's endo, right? Okay, so if we look at the hydrocarbon here, the hydrocarbon is going to be either pointing, if it's pointing away from the double bond, then it is exo. If it's pointing towards the double bond or parallel to the double bond, then it's endo. So in this case, double bonds here, this guy is pointing away from the double bond, the R group. So it's considered, since it's pointing out, it's considered to be an exo, where this guy is endo because it's not pointing away, it's not going in the opposite direction of the double bond, it's in the other plane. So endo products are going to be formed faster. And that's when our substituents have pi bonds or pi electrons, sorry, not pi bonds, pi electrons. Sorry. Okay, so this would be an endo transitional state. This is an exo transitional state. So we can see the hybrid structure here. It's pointing towards that hybrid structure where this guy is pointing away. So exo again away, endo towards or in parallel. Okay. So Okay, so here are two structures. So these are going to give us, so we have an asymmetric center. So then we're going to end up with a racemic mixture in this case. Right, so we have, in one case, there's our asymmetric center. So we have it pointing down, in this case, pointing up. So 1, 2, 3. Okay. And you guys can see how both are going to be formed. Who's going to have, since it's a racemeric mixture, what does racemeric mean again? You're thinking, yeah. Do you guys remember what racemeric means? Okay. You guys remember polarity? Using, okay. So when we talk about how it would polarize, so in the curve, you had an S and an R. You guys remember that? And the distinction between S and R, although they're going to behave very similarly, right? It's just how they're polarized is going to be a distinction. So these guys are going to behave similarly, but one of them is in the S formation, and one of them is going to be in the R formation. Okay, and so the only distinction between them is how they're going to polarize, right? So, and that's using the polar cell. Do you guys remember that? Polar cell, like using light to get the, yeah. And the other one going the other way, yeah. Okay. So in this case, if we have a reaction that can creates two asymmetric centers, right? So we have this structure that can form, right? And then we have so we have cis products, right? It's mirror image. And then we also have trans products, where this guy is going towards you, and this one is going this way, one is going that way, right? Okay, so in the case of our trans, we're going to have these trans products generated. So again, we're going to get the reaction occurring here, right, to get that ring structure. But these guys are going to remain in trans, where these guys are cis to each other. So they're going to remain in cis, but you're going to end up with mirror image forming. Okay, so cis forms cis, trans is going to form trans. The only thing is that you're going to get racemers that are going to be forming those, right? Mirror images of each other, complete mirror images of each other. Okay, let's see. How we doing on slides? What time is it? Okay, so we're doing pretty good. So let's take a 5-minute break and then we'll come back. Okay, so we have a pretty good idea of how to determine your reactants. So let's say we're given a product and they want you to determine what the reactants are. And so it's just going to be working backwards. So the first thing that we want to do is we're going to add the pi bond. We're going to delete this pi bond. So this guy gets a pi bond, this guy gets a pi bond. And then this bond is going to be deleted. So then we know that we have our conjugate diene, and then we have the other product. Okay, so here, in the case of our bridge, so we're going to add a pi bond. So we'll get this. So then we know that this bond is going to be deleted. So then we know that we're going to have a ring structure, right? Here we just show what the ring structure is. We drop the bridge, right? And then this here would be the other product. So we can work back to determine the reactants of a reaction, okay? How are you guys doing? Okay, so let's see if we can, let's see what we can do here. No. Okay, let's say we had two. Yep, we're going backwards. Not finished. Actually, let's do this. Oops. Sorry, I'm trying to make it. There you go. Bless you. Bless you. Bless you. Okay, there you go. So what are going to be the products? Bless you. Mm-hmm. Yes. Don't make fun of my methyl. Special methyl. Okay, bless you. Okay, I'm giving up. What's that? He's allergic to the problem. Yeah, that's true. As soon as I mention it, they just start sneezing like a. Yep. It's not that it breaks down. You're trying to determine what the initial reactants are, right? So what's going to produce this product? What are going to be your two? What are going to be the possibilities that you have to produce this product? Maybe. Okay, got some answers? So, yeah. Okay. What do you guys think? One of the products is going to be what? Okay. So our conjugated, yep, conjugated diene and can you draw your answer on the board? Okay, just tell me what would this bond be here? It's a triple bond. Okay. So technically it should be, that's right. Triple bond, and then okay, so that's 1, 2, 3, 4. 4 carbon chain, butene, buta, yeah. Or we could say, yes, it would be butane. So we'd have to put buta. And then where's the ine? Where's the in? Okay, so it'll be 2. And then double bond OH. That'll be called what? No, when you use oxy, oxy means that there's an O in between 2 hydrocarbons. So that would be ethers. So this is not the ether group. This is, you guys should know this from, nope, it's not a ketone. It's a carboxylic. And so what is the abbreviation for carboxylic? Oh, acid. Or you could just say it to view. butene acid. Yeah. Okay. Okay. Okay, so when we talk about stability, right? Can I erase? Okay. Okay, so when we talk about stability, this here is the potential energy. And then, so when we have delocalized electrons, it's going to make it more stable. Okay, so cyclohexene, right? So this is the delta H. It's going to be negative 200, negative 28.6 kilocalories per mole. So when we have cyclotriene, in this case, these electrons are going to be localized. This guy's going to have a higher delta H of negative 85.8 kilocalories per mole. This here is cyclohexane. Okay, so we're basically going from hexene to hexane. Hexane will be that ground state. Okay, and then here's benzene, right, where we have delocalized electrons. So, and that is going to have an enthalpy of negative 49.8 kilocalories per mole. And then going from the localized to delocalized, that's going to be a change in 36 kilocalories. So if it's localized, it's going to be more energy associated with it than in the case of it being delocalized. Okay, questions? Concerns? Okay. So the criteria for something to be an aromatic ring. So we're getting into aromatics. Aromatic basically stands for aroma, right? Smell. So it's going to have a pleasant smell associated with these guys. The criteria is that it has basically a benzene ring, right? Or we have a benzene pi cloud in this situation. Okay, so benzene basically has 3 pairs of pi electrons. And we know that it has to be delocalized because that's going to be the more stable version rather than it being localized. Okay, so in this case, it must be an uninterrupted cloud of pi electrons. So that's essentially what we're showing here, uninterrupted cloud. So in other words, these guys are going to be interacting with each other, okay? Because you're having the electrons going from one place to the other, right? So that movement of those electrons. Okay. So these guys are not considered to be aromatic. So cyclobutadiene or cyclooctatetraene. So neither of those are, because they're going to have even pairs of pi electrons. So they have to have odd pairs of pi electrons for them to be considered to be aromatic. Okay, so here we have cyclopentadiene is considered to be non-aromatic. So we have cyclopentadienyl, the cation, that is also going to be non-aromatic. Where we have cyclopentadienyl anion, that one is going to be aromatic because it has an uneven pair of pi electrons. Okay. So how do we know that the low pair are pi electrons? So this is just showing us the resonance structures, right? So then in this case, the electrons are going to be donated to here. This is going to cause the delocalization of this guy, which is going to in turn, well, this one is already going to be delocalized. So then we're going to get the sharing of the electrons around the entire ring. Okay. Questions? Concerns? Cash? Okay. So, naphthalene, these are some aromatic component. Phenylanthrene is another aromatic component, and then pristidine, another. So naphthalene is basically, it's almost like it's a benzene ring with almost a benzene ring, right? So, was that? It's a bridge, yes. It's not fused, or is it fused? Remember bridged? So this one is actually fused. Yeah, it is fused. So remember, we'll go back. He is correct. So bridge, right? And then fused, right? You see the distinction? Okay, here. What else did I want to say on this? There's something else. Now I forgot. Okay. Well, these are aromatic components, right? Again, we're starting off with that benzene ring that is going to make them smelly, right? And then in this case, you know, we have the benzene ring, but then these guys technically will be also benzene ring here, right? Because that's 3, okay? Delocalized benzene ring and benzene ring. So this guy is basically a combination of 4 fused benzene rings. Where this one isn't, right? Although it's gonna have, well, the benzene ring is delocalized, right? So it's gonna be sharing, so it's gonna be kind of acting like this one is. This one is, though. Okay. You see the distinctions between them? Yay, nay, yeah. Questions, concerns? So these are the molecular orbitals of aromatic compounds or aromaticity. So in this case, these are going to be our bonding. These are our anti-bonding. And so our energy level, so in the case of our ring structure here, it's going to have odd pairs of pi electrons. Right? And so, and that's the same thing that happens here in the 5-ring structure. And if we added that extra electron onto it. Okay. So in that case, the pi are going to fill the bonding regions, right? So instead of the anti-bonding regions. Oops, sorry. Okay, so anti-aromatic compounds. So if anti-aromatic compounds, things that are going to be filling the anti part of the regions, those guys are going to be less stable than things that are going to be cyclic compounds with localized electrons. And then aromatic compounds are going to be the most stable. Okay, so if we have an even number of pi electrons, we know that that's going to end up causing us to be stable or unstable. Stable, are you sure? Pairs. So if we have an even number of pi pair electrons, I'm not saying just even number of electrons, an even number of pi pair. What's that? Is that going to be stable or unstable? That's going to be more unstable. So remember, it has to have, for stability, I mean, not stability, for pair, where is it? Okay, so non-aromatic has even pairs of pi electrons, where aromatic, okay, so it's going to have an odd pair. Okay. Okay, so, but we know that even numbers, and that's what they're saying about so an anti-aromatic compound fulfills the first criteria for aromaticity, but has an even number of pi electrons, right? So in other words, it acts like it fills that lower molecular orbital, but you have extra that go into the anti. So like here, we have electrons that are going to end up in here, but you have the even number of pi electrons. Okay, does that make sense? So do you understand what I asked you? And then the question I asked you, and then what we just talked about with the anti-aromatic compound? Okay, so when it's anti-aromatic, it basically, it fulfills the first requirement, right? Criteria, meaning that you have 3 pairs or odd pairs of, odd pairs of electrons, right? But you have, if it's so in this case, that's 1, 2, 3. That makes it aromatic. With this guy, it has 1, 2, 3, and then it has an additional extra, right? And so that makes it anti. So it has an odd, it has even number pairs of electrons, right? So it met that first criteria, but it went extra, right? Does that make sense? Okay. So in this case, if I had, because we know that when it fills, it's going to feel like this, right? Where we have an electron here, an electron here. So this are even number of pi electrons. But this guy would be anti-aromatic rather than aromatic, where if it just had this here, it would be aromatic. It doesn't make sense. Let me see. Yeah, if I had extra, if it's B is aromatic right now, yes, because it's just showing you we have it filled and we have the extra lone pair that's added onto it, right? So these both meet the criteria of being aromatic, right? So anti-aromatic basically means that you go into the anti-bonding part, right? And you have an even number of electrons. So when we fill electrons, they'll want to go here, want to go into the next anti-orbital, right? So it's still 2 electrons. It's an even number of electrons totally, right? So we have a total number of pi electrons that are even, right? But because they went into the anti-region, that's going to make them anti-aromatic, okay? Where these guys, we have an odd number, and this is also an even, well, this here would be an odd number of paired pi electrons because these are paired, right? And so this is what makes them aromatic, that pairing, okay? And also that benzene ring, essentially, because that's what the benzene ring is going to be consisting of, is that pairing in this case. And then in this case, it's just that extra lone pair of electrons that we've had. Okay. Okay, so how are you guys feeling so far? Now let's change that definition a little bit because we've been associated with just that benzene ring as being aromatic. Well, these guys are called heterocyclic aromatic compounds. So they're heterocyclic. Why do you think they're called heterocyclic? Because it's not all carbon, right? So far, what we've basically defined in terms of our aromatic rings have been carbon-based rings. In this case, they're heterocyclic because now we have another element other than carbon there, okay? So pyrimidine, this is pyrrole, this is furan, and this is thiophene, okay? All are aromatic rings because they meet that criteria. They'll have an odd number of odd pair of pi electrons, okay? So this here is going to be the orbital structure for pyrimidine. So these guys are going to have equal distribution of, so they're going to be kind of fusing together, right? So you're going to get an equal distribution of the electrons along that ring. And then this guy here is going to be able to have a sigma bond interact with it, okay? Here's the orbital structure for pyrrole, okay? So here, and then we have the hydrogen actually interacting with that. And then here's the structure for furan, okay? Okay, so these are going to be our contributing resonance structures. So here we have the electrons being donated here. So we get a double bond here plus here. Then that causes this electrons to be moved here. So then this guy has a negative charge. So we have the positive and negative separation here. So then what would be the equivalent? Another contributing is where we would go with the electron going the opposite way, the other direction, right? And then, and that would give us this guy. And then we have the case where we have the, let's see, this bond move this guy move here, then move this guy here. So then we end up with this structure, and then the opposite of that one as well. Okay. So, and this is the case for purol, very similar process. Plus minus, plus minus, plus minus, plus minus. So these are all the different resonance structures. And so we'd get that hybrid structure of where we'd get minuses being distributed out the entire ring compound. Okay. So in this case, this is benzene. So we get the equal distribution, right, of the electron cloud. In the case of the nitrogen, I mean the pyrimidine, where we have the nitrogen at the end. So in this case, we get these guys are going to be equally distributed, but we're going to end up with electron withdrawal on the nitrogen part. Right? And then here, in the case of the pyrrole, we're going to get pretty much an equal distribution, but then we're going to get nitrogen is going to be able to donate electrons into the ring structure. Okay. So these are more examples of aromatic heterocyclic compounds. So we have quinoline, we have indole, we have imidazole, and then we have purine, and then we have pyrimidine. So if you guys notice, pyrimidine and purine, these are, well, all of these are components that are going to be found in the human body. These are part of the base of your DNA structure, the purine and the pyrimidine, right? So in terms of, you guys DNA, familiar with DNA? A and, okay, so your pyrimidines were G and C. No, G and C match up, but no, your pyrimidines are G and T. And then your purines are A and C, I believe. I have to look at the structures again, but we'll be going into that at some point. So. Okay, so how benzene reacts. So here, this is going to be our electrophile. So in the case of where we have an electrophile, we're able to substitute one of the hydrogens for that electrophile. Okay. So this guy would be called an aromatic substitution. Okay, so here we would get let's see. So the very first step of your aromatic substitution is your double bond is going to be contributing the electrons to that plus charge. So then that's going to get your binding there. So this is going to form our carbon cation intermediate, right? And then, so in the case of our non-ring structure where we have our double bond, so then we're going to have the double bond again contributing to that. So it's going to be very similar to what happens here, right? So we're going to get the Y attached to that carbon there, that inner carbon. And then we're going to have Z minus, and then that Z minus is going to attach where that plus is at. So that's what's going to happen in that case. So we're going to get the formation of that carbon cation. Is it time? What time is it? 5:47. I got 3 minutes. Okay. So in this case, again, double bond contributing to the Y. Y is going to attach. And then we're going to have our Z being able to add here or here, right? So it's going to contribute its electrons here. Then it's going to allow this guy to end up being released. So we're not going to get the formation of our non-aromatic ring in this case. We're not going to get A forming, but instead, we're just going to get the electrons being contributed here. So then the hydrogen is going to be plucked off and allowing the double bond to form. So we're just going to get the reformation of our double bond. Okay. So we're not going to get the formation of the electrophilic addition. Instead, we're just going to get an electrophilic substitution. So we're just going to get that the Y being added on. Okay. So we'll stop here. We'll pick it back up